So what we're looking at today is 1.2 part 1, reflections. Graph the resulting function if an original function is reflected across either of the two axes. So I'm going to go under the assumption right now that you know what the x-axis looks like. It's this. It's the horizontal axis. And the y-axis looks like this. It's the vertical axis. Determine the resulting equation or graph of a function if we know the original function and the type of reflection. And then it turns out that there are going to be this new thing called an invariant point. When you take a function and you do to it what we've been talking about for 2 and a bit days of classes, every point moves. Every point finds a new home. An invariant point is a point that after the transformation, not necessarily a translation, in fact not a translation, after the transformation, if a point ends up being where it was to begin with, in other words, it's not affected, it's called invariant. So a reflection is a transformation that flips each point across what's called a line of symmetry. Okay, if I were to just look at my two hands, this hand is a reflection of this hand across this line. Right? And I've got something up here to show you in a second. So when I say flip, I mean it kind of pulls out into 3D space and rotates 180 degrees and lands back in the same plane. That's what I mean by flips. And I want you to imagine this line of symmetry going down my body from my nose all the way down to the point halfway between my feet. And I want you to notice that if this is a perfect reflection, the distance between the tip of this thumb and the line of reflection, or line of symmetry, and the distance from the line of symmetry to this thumb is the same, right? So when you look in a mirror in the morning, in a plain mirror, you know, the tip of your nose is just as far away from the mirror as the tip of your image's nose is from the mirror in your brain. Because you understand there's nobody behind there, right? Okay. So what we're going to be looking at today are those reflections. Points that are on the line of symmetry would not move. So if the line of symmetry is here and I put my hand right there, then the reflection will look like that. And the tip of each thumb is touching. They're touching each other. So it's invariant. It didn't reflect. This reflected to here. This reflected to here. This reflected to here. But my thumb tip, just the point, did not reflect. So that's invariant. Today you're going to be looking at, and I want to pause here and I want you to mentally digest this, because there is going to be something that you will mix up. Many of you will mix up. So much so that I can mention this twice a day until we write our exam. I can mention it right before I hand out the exam, and some of you will mix it up on the exam. Okay? And it's that a horizontal reflection is across the y-axis, which is counterintuitive because you see the word horizontal and your brain conjures up the x-axis because that's the horizontal axis. If you were to go back, and I will show you something on the screen in a second, go back and look at this example that I've been referring to, would you agree that to reflect this hand to here is a horizontal change? Okay. Well, the line of reflection is a line coming down the center of my body vertically. So a horizontal reflection is across a vertical line. Similarly, a vertical reflection is across a horizontal line. There's a third type of reflection that we're going to learn about later on. But these are the two reflections we're going to focus on. So just forgetting about your notes for a second, because this isn't a function, this is just a picture. There's a picture of some kind of goofy smiley face, happens to be in quadrant 2, and I put it up here as well. If I do this to it, it's a horizontal reflection, right? Okay. It's across the y-axis, correct? There's the y-axis, you can see it's across it. Now, here's where you can double psych yourself out, because the equation of the y-axis is x equals 0. A horizontal reflection is across the y-axis, but the equation of the y-axis is x equals 0. That's how easy it is to mix up the coordinates here. Are 0, 4 and 0, 2. These points have x coordinates of 0. Right? It's not to the left, it's not to the right, it's at x equals 0. If you take a look at the second image, that's a vertical reflection. A vertical reflection is across the x-axis. You can see that, right? Things above the x-axis go below the x-axis. But the equation of the x-axis is y equals 0. You guys with me on that? And even to get something good out of my mistake that I made a second ago, even when I do these, I double check at the very end. As I teach this, I always say it, and then I go, in my head, you can't see me thinking, but I'm thinking, is that right? Okay. If I were to reflect this horizontally, this is what it would look like. Are we in agreement on that? Okay. You will notice that there are 2 points that didn't move. And the way I like to describe this is to say, for a horizontal reflection across the y-axis, any point that's to the left of the y-axis is going to be to the right of the y-axis after the reflection. Any point that was originally to the right of the y-axis is going to end up to the left of the y-axis after the reflection. So any point on the y-axis is not going to move. So that would be an invariant point. I hope it's clear that this would have 2 invariant points as well. So are you with me on the general idea of what a horizontal reflection is, what a vertical reflection is, and what invariant points are? Okay, let's get back to the handout now. Example 1 gives you a function, and what you were asked to do, I just want to make sure your graph is the same as mine. It is. What you were asked to do is sketch the resulting function if this is reflected across the y-axis, and then do something else. So what we do here, everybody, is my advice is to do this in a systematic way by starting on one side of the original function, reflecting the point, and then moving to the next point on the original function and continuing that process. So this particular point on the original function is 4 to the left of the y-axis, so when it reflects, it will be 4 to the right. And then what I'm going to do is move on to the next point, which is 2 to the left, and if I reflect it across the y-axis, it will be 2 to the right. And then I can draw that segment. What I'm really telling you, everybody, is that this piece of the graph reflects to this position. And then I continue. My next point happens to be this one. It happens to be 1 unit to the left of the y-axis, so I'm going to reflect it 1 unit to the right, and then I connect them again. And I just continue in this fashion until I'm done. It's not a difficult process. My next point is this one. It's 2 to the right, so when I reflect it, it will be 2 to the left. And my final point, well, there's lots of points, right? I could, everybody, reflect this point, and this point, and this point, and this point. But since this is a straight line segment, I'm just going to go with the end point of it. That happens to be 5 to the right, so when I reflect it across, it's going to be 5 to the left. And this is what it looks like. So, is there an invariant point? No. It happens to be here. I'm going to identify it just by highlighting it. You can identify it however you like, but that happens to be the invariant point. What type of reflection is it? It's a horizontal reflection. across x equals 0. And I have to think about that. That doesn't just come out of my brain. There's a lot in math that you and I it just comes out. It's a fact. We don't even need to think about it. I immediately said to myself, I'm visualizing something in my head. Maybe I'm visualizing this. A horizontal reflection is across this line, which is the y-axis, but that's where x equals 0. I could have said across the y-axis, but to be honest, I just ran out of room to write. So that's why I said across x equals 0. Why is this y-intercept invariant? Because it's on the line of reflection. First and foremost, that's the most general answer to that question. An invariant point is going to be any point that's on the line of reflection, because if it's on one side, it goes to the other, and if it's on the other, it goes to the one. So the only way it can't move is if it's not on either side, which means it's on the line. Does anybody have any questions about this first example? Pretty straightforward, I hope. Well, let's do the same thing to the same function, except the reflection this time is going to be across the x-axis. Well, that means that things that are above the x-axis will reflect below, and things that are below will reflect above. In other words, it's going to be a vertical reflection. This point happens to be 4 below. No, it isn't. 3 below. So it's going to reflect 3 above. The fact that you saw me drag that point 3 above, I don't want to give you the impression that it's being translated. It's disappearing from where it was and appearing above. Okay. Where are we at now? The second point, left to right, is this one, which is 3 below. It's also going to be 3 above. And that means, of course, that this will be that line segment. And that makes sense. You can see that that horizontal blue line segment at the bottom gets reflected above. The next point that I have, left to right, is this one. It's 0 above or below, so it should be invariant. It's not going to move. It's not below, so it can't reflect above. It's not above, so it can't reflect below. So we can connect that. I can go on to the next point. I did this one, this one, this one, and this one. This is 2 above. It needs to reflect 2 below because it's a vertical reflection. And finally, this point is 1 below. It should go 1 above. Now, I hope you see that if you do a good job here, when I draw the line segment, it should pass through this point, shouldn't it? Because that point needs to be invariant because it's neither above nor below. You know, we're not landing people on Venus. It doesn't have to be perfect, but you can see that it's invariant. So the invariant points I've identified, if you like, we can actually put a point here. It doesn't matter. Every point is a point, even though there's not a blob there. And we can say the type of reflection is a vertical reflection across. Now I got to think about this. It's a vertical reflection. That's across the horizontal axis, but the equation of the horizontal axis is y equals 0. Y equals 0, y equals positive, y equals negative. The horizontal axis is at y equals 0. Does anybody have any questions with that example? All right. So we're going to explore something here. Let's consider this quadratic function of x squared minus 4x minus 5. The first little thing that we did was simply to get you used to the idea of what a reflection is and what invariant points are. So it says, write the equation of g of x if g of x is equal to -1 times f of x. So what does that mean? It means we're going to take -1 multiplied by the entire original function. So g of x will be -1 multiplied by x squared minus 4x minus 5. Let's simplify that. I don't think we want to leave it in factored form like that. We can multiply that negative 1 through and get the equation of g of x as negative x squared plus 4x plus 5. Are you with me on that? Okay. While we're doing that, let's do the same kind of thing over here. Okay. We're in that mode of doing some algebra. Let's do that. We'll worry about the graphs later. So what is this saying? This is saying we want h of x equals f of negative x. Well, if f of x is x squared minus 4x minus 5, f of 3 would be 3 squared minus 4 times 3 minus 5. F of negative x is going to be this. Whoops. It's going to be that. It's going to be the result of replacing x in the original function f with negative x, because we want to find f of negative x. And similarly, we want to simplify that. I really want to stress to you that in order to minimize the number of mistakes that you make, it is important for you to get in the habit of always putting anything that's substituted into anything mathematically in its own set of brackets. Sometimes it's not necessary, but it's necessary enough of the time that if you just get in the habit of doing it all the time, your mistakes will be minimized. You're going to make mistakes in math. We want to minimize the number you make. So when I square a negative quantity, it becomes positive, which means h of x is x squared. Negative times negative plus 4x minus 5. So this is the equation of h of x. And what we are asked is to compare, we'll start with this, is to compare g of x and f of x. So the question is, what happens to a graph of a function if we multiply the function by negative 1? Well, let me show you. There's the graph of f of x. You can see the equation of f of x up there. It's x squared minus 4x minus 5. And here is the graph of g of x. Now, I don't have the luxury of or the time to change it to g of x. I've just got f of x up here. But you need to understand that negative x squared plus 4x plus 5 is what you have written for g of x in part A of this question. Right? And you will see that there's a vertical reflection involved. That the vertex of the original function, which is at 2 comma negative 9, there's a little red point at the bottom you can see there, ends up going to 2 comma positive 9, which you can see at the top. And that's an important little observation. The y coordinate of that point went from being negative to positive. I can show you another point. 6 comma 7, this point up here that I'm indicating is a point on the original function, and it ends up being down here, 6 comma negative 7. I hope it makes sense to you that the y coordinate is opposite, because a vertical reflection involves transferring that distance above to the same distance below, or vice versa. Okay? So we can write down the conclusion here. They are vertical reflections. What about h of x and f of x? So now it's asking us, if you take a look at a function, f of x, and you change every x to negative 1 times x, what happens to the graph of the function? Well, let me show you. I mean, I think you kind of know where this is going, but... So I'll pull this one up here and you can see that I haven't simplified this, but I'm trying to drive home the fact that this is where we replaced every x with negative x. You can see that it is a horizontal reflection, right? If I take a look at these 2 points, negative 1 comma 0 is the original point on the function, and then the transformed or reflected point is at 1 comma 0. Give some thought to the fact that when we had the vertical reflection, that's the vertical reflection, and I didn't multiply the negative through here, it's still there, that it's the y coordinate which gets multiplied by negative 1, right? 1 comma negative 8 becomes 1 comma positive 8. The y coordinate gets flipped. And by the way, I don't have it. Why don't I have that? Oh, there it is. By the way, this point, which is at negative 1 comma 0, doesn't move in a vertical reflection because the y coordinate's 0. And if you multiply 0 by negative 1, you still have 0. It doesn't change. So we're multiplying y coordinates by negative 1, whereas when you take a look at the horizontal reflection, we're multiplying the x coordinates by negative 1. So what's the conclusion here? These are horizontal reflections. And I'm just, for the sake of brevity, which means to save a little bit of time, I'm not going to be writing all the time in class horizontal reflection across the y-axis, which has an equation of x equals 0. But if you're writing an exam and it's a written response, that's what you should put. You should demonstrate to the marker, whether it's a marker in Edmonton or me, that you know what you're talking about. Are there any invariant points, and where are they? Well, I mean, I could just summarize this by saying there will be invariant points anytime there's a point on the line of reflection. But let's be more specific here. We've got the horizontal one, I think, pulled up right now. The invariant point on the horizontal is this point, 0 comma negative 5. Why is it invariant? Well, because it is neither to the right nor to the left of the line of reflection. Any point to the right will reflect to the left. Any point to the left will reflect to the right. So again, we come to this general idea, which is very important for later as well, that during any reflection, a point on the line of reflection will always be invariant. It happens to be the y-intercept, because the y-axis is the line of reflection. So, yes, it happens to be the y-intercept. And it's, again, I'm not going to write this down, but that happens to be on the line of reflection. That's what's most important here. The y-intercept is on the y-axis. And if I take a look at the vertical reflection, which looks like this, are there invariant points? Absolutely. Unfortunately, I don't have them all here. I only have this one. There's another invariant point over at 5 comma 0, right? So why are those 2 points invariant? Because they're neither below the line of reflection, in which case they would go above. They're not above, so they can't go below. They're on the line of reflection. But more specifically, there are 2, and they are the x-intercepts. There's something which I call autopilot in math. And I get in autopilot sometimes where it's kind of scary, actually, because I'll be teaching and writing a bunch of stuff, and then I'll look at what I've written, I'll go, I don't remember writing that down. Like, I don't remember thinking about it. It just came out. I would say the lesson we're dealing with today is something you do not want to get on autopilot with. You want to think about this every time it comes up. Write the mapping that describes what's going on. Well, we've already talked about this. For the vertical reflection, what's happening to every point is this. The x-coordinate is staying the same, and the y-coordinate gets multiplied by -1. And that works even if y is 0, because if y is 0, which means it's an x-intercept. 0 times negative 1 is still 0. It's invariant. It works. Okay? And the mapping here is that x becomes negative x and y stays the same. Now, it's possible that you reflect vertically and horizontally, in which case x gets multiplied by negative 1 and y gets multiplied by negative 1. So let's do a quick summary here of what we've learned, and then we have a few examples to do. So vertical reflections are when you change a function from f of x to negative f of x. Vertical reflections happen across the x-axis, which is y equals 0. You might see, instead of across, you might see over the x-axis, or in the x-axis, or about the x-axis, or relative to the x-axis. There's different ways we can describe it. The mapping is this, because vertically means y changes, and the invariant points are any x-intercepts, because x-intercepts are where y is 0. And again, that requires some thought. For me anyway, there might be the odd person that just has automatically accidentally memorized all this, but I'd be leery about relying on your memory. Horizontal reflections happen when you change a function from f of x to f of negative x. They happen across the y-axis, which has an equation of x equals 0. The mapping is that x changes to negative x, and an invariant point would be a y-intercept. Notice I just say invariant point here because functions can only have one y-intercept. They can have multiple x-intercepts, but only one y-intercept. So let's take a look at some examples. Write the equation of the resulting function under each transformation. So the function is reflected vertically. If the function is reflected vertically, based on what we've learned, one of these is correct and one is not. You have to be, this is maybe the memory thing. This is maybe the only memory thing in this lesson. You have to know which of these is a vertical reflection and which is a horizontal. And the way I think of it is, to me it's obvious because the bottom one, the second one, has a negative in front of x. That's telling me x is being multiplied by negative 1. That's horizontal. So it's not this. A vertical reflection is this. And all this means is that the new function will be negative 1 multiplied by the original function. That's it. That's all we have to worry about. So the new function is g of x is negative 1 times x minus 3 over 4 minus x. Now let's talk about negatives and fractions. Is this correct? Sure. Don't do that though. Take that negative and multiply it through on the top. Okay? So if I do that, I'm getting negative x plus 3 over 4 minus x. That's the equation of the reflected function. And if you want, if our classes were back to the old time, I would do this. We could easily sketch f of x and g of x. And although you might not be familiar with what these things look like, it might be a bit of a surprise, you would discover they are vertical reflections of each other. On the other hand, when I take a look at b, b says we're going to take that function and reflect it horizontally. Well, a horizontal reflection means the new function is found by taking f of negative x. So we are going to write the original function, and every place we see an x, we're going to put negative x. It's very easy to make mistakes here. You're dealing with negatives and brackets and subtraction signs. And again, that's why I recommend you putting in your substitution of negative x in its own set of brackets each time. I mean, you don't need this set of brackets on top. You really don't. But you need it on the bottom. So if you need it sometimes, just put it in all the time. painting myself into a corner here, didn't leave myself enough room, that's okay. So I'm going to simplify this and write negative x minus 3 over 4 plus x. Capiche? All right. F of x equals 3 to the 4x is reflected in the line x equals 0. So I'm switching it up a bit. I'm not telling you whether it's a horizontal or a vertical reflection. I think you should know, I hope, I mean, this is the starting point. This is, again, the only thing that I think you need to memorize or be able to sort out fairly quickly. I think you should know that negative f of x is the vertical reflection of f of x, and f of negative x is the horizontal reflection of f of x. But now you have to decide which of these two reflections it is. And you have to think. X equals 0. Okay, so if the center of my sternum is the origin, x is negative over here, x is positive over here, x is equal to 0 dead center horizontally, which means we're talking about across the y-axis. But now I can visualize that across the y-axis is in fact a horizontal reflection. So we're talking here about in C, this. So we substitute negative x in for x in the original function. Nobody writes 4 times negative x. We would write negative 4x. Okay with that? Okay. Final one, this function is reflected in both axes. So what that means is that the new function, after a horizontal reflection, would be this, but then if we're going to reflect it vertically, we have to multiply that result by negative 1. So we have to apply this twice in 2 places, or 2 ideas. So I'm going to leave the negative 1 out here, and I'm going to put in here, I'll even write an extra line, f of negative x. So I'm going to have g of x equals negative 1 times this function f of x with a negative x every place there's an x. And what this question is really a test of your ability of doing is working with negatives, because we've got negatives all over the place. Inside of the set of brackets, a negative quantity cubed is still going to give us a negative term. Right? Negative x times negative x times negative x is negative 1 times negative 1 times negative 1, which is negative 1, and then times the x times the x times the x. We have minus, and negative x quantity squared is x squared. And then we have plus negative x, and we have plus 6. And now we can take that negative 1 out in front and multiply it through everything. So the function will be positive x cubed plus x squared plus x minus 6. So again, we put negative x in for x everywhere to begin with, clean that up, and then multiply everything by negative 1. And I just want to check my work here. Negative, positive, positive, positive. So negative x cubed, negative x squared, negative x, positive x. We're good. Okay. We have one more problem set to do. And I'm really glad we had this conversation with the question that Abby had asked about earlier, that I think it was number 10, I think, where we had that linear function which was translated and we had to find the parameter. I said there are many different ways to do some of these problems, and sometimes one of the methods is better. And I think the best method for this question is not to worry about algebra at all, to just worry about what's happening. I think if you introduce mapping and algebra here, things get confusing. We've got this point, 4 comma negative 9, and if you like, you can visualize where it is on a grid. You could even draw it on a grid if it helps you. Where will that point be on g of x if g of x is negative f of x? Well, it's a vertical reflection. I should know that negative f of x is a vertical reflection. And I should know that that means if it's below the x-axis, it's going to go above. And that leads me to the conclusion that the coordinates are going to be 4 comma positive 9. The y-coordinate is going to change from negative 9 to positive 9. You guys with me on this? Okay. On the other hand, if I take a look at h of x equals f of negative x, well, I should know f of negative x is a horizontal reflection. So, I mean, I don't need to look at this. I should be able to just imagine 4 comma negative 9 reflecting horizontally will give me negative 4 comma negative 9. Does that make sense? I could use mapping. I could say for a horizontal reflection, x comma y maps to negative x comma y, and then just multiply the x coordinate by negative 1. But I don't think it's necessary. Any questions with A or B? I'm sensing a lull in the room. Is that because you get this? It's easy? Okay. It's like you guys are unsure about something, but maybe that's just me this morning. Okay. What about k of x equals negative f of negative x? Well, that means we reflect things horizontally and vertically. You can go back to this point if you like, and you can say, well, if I reflect it horizontally, it goes here, and then if I reflect it vertically, it lands here. But the bottom line is both the x and y coordinates have been multiplied by negative 1. They're opposites. So if it was at 4 comma negative 9, this will be at negative 4 comma positive 9. And then just to keep us on our toes, D has nothing to do with reflections. And I apologize for having 2 k of x's. How embarrassing. I should have used a different letter. Doesn't matter, though. This means we shift 7 to the left and 8 units up. This is just an abbreviation. You would never write that on an exam. You'd write it out in words. So where was I? I was at 4 comma negative 9. Is that the ordered pair? Okay. So when I shift that 7 to the left, I get negative 3. And I shift it 8 up, I get negative 1. Negative 9 plus 8 is negative 1. Even though, I think, even though the questions you're going to be working on that use what we learned about require a lot less work than any of the stuff we've done prior to today, I think it requires more thinking at times here. To try to, suss out, which means figure out, what are we talking about here? Are we talking about this reflection or that reflection? What does the line y equals 0 mean? Because some of you will get into this bad habit. You'll say, well, I know it's opposite, so y equals 0 must mean a horizontal reflection. Y equals 0 is the x-axis, which means it's a vertical reflection. It's complicated. So you have some questions to work on for tomorrow. Get started. You've got about 10 minutes here to work on them, I think, roughly. And I'll make a quick trip around the room and check on you.